Leibniz was sending letters back and forth to a guy named Samuel Clarke. So not to Newton himself, but this follower of Newton named Samuel Clarke, who was an English theologian. And this is what they argued about. And Leibniz said, well, you know, you have the creation at, I don't know, whatever, noon on such and such a day, but why at that time? Why not 10 minutes earlier or 10 minutes later? This was something that philosophers call the principle of sufficient reason. That to have it at some time and not another time would defy any possible reason, and that's illogical because God would have to have a reason to do something. And I mean, I've read different philosophical critiques of this. One modern philosopher compared it to his undergraduate students who don't particularly feel like getting up in the morning, but eventually they do. Not for any reason, just because you have to get up eventually. And so maybe the creation of the universe is something like that, and God just thought, well, you know, might as well get on with it and do it. But I raise this just to show that even back in Newton's day, and that definition seemed kind of intuitive or logical, but it does raise problems, and in Newton's own lifetime it raised all these objections. So what was God? Was time passing? Newton says, yeah, sure, that's a reasonable thing to say. Leibniz felt that doesn't really make any sense, and the more logical viewpoint is that God must have created time together with the universe. Leibniz is not the first person to suggest that. It goes back to Augustine, for example, the famous Christian theologian, I think in the 4th century AD. And of course, it doesn't end with them. I'll talk later about the Big Bang and sort of the modern equivalent of this argument, which is still going on. Okay, some other puzzles. Newton's equations are what we would say are time symmetric. So the equations themselves don't tell you which way time goes. Time appears in these equations usually as a parameter. You're thinking, well, when I was in high school or junior high, we learned all these formulas. Yeah, you did learn all those formulas. You know, you have a car speeding along at 60 kilometers an hour after 2 hours, how far has it gone? So time is a parameter in those formulas. But there's nothing in the equations that gives you the flow or the direction. I mean, there's nothing that tells you why time should move along in any particular direction or at any particular rate, if it is in fact even meaningful to speak of those things. Yeah, why does time have a direction? There's nothing, I mean, as far as Newton's concerned, there's no answer to that. People began to talk about this idea of the arrow of time, and maybe you have an intuitive feel for what that means. I mean, if you watch a movie backwards, typically you can tell you're watching it backwards. And Arthur Eddington used this phrase, I think, in the late 20s, the arrow of time. So I mentioned a movie. Yeah, usually you can figure out in what order a sequence of events happened in. Not everything, in the practical world, not everything is reversible, even though Newton's equations themselves are. I mean, the equations can distinguish past and future. So what's going on here? There's something kind of subtle going on. And at this stage, and I do have to talk about some physics. I hope it won't be too painful. But I know if I leave out entropy and the second law of thermodynamics, at least some of you will think I've shortchanged them or that they haven't got their money's worth. So I will talk about it a little bit. So entropy is a measure of disorder, roughly. I mean, actually, the physicist's definition of entropy is a bit complicated. But roughly speaking, it's the amount of disorder or disarray in a system. And the second law of thermodynamics says that if you have a closed system, so that stuff isn't going in or out of it, the amount of disorder is always going to increase. And one way to illustrate that is, these things allegedly explain the arrow of time. Maybe, sort of. Well, we shall see. Imagine a container that has these two chambers in it, and there's a divider, but we'll remove the divider in a moment. So I've just called them A and B, and they're perhaps different molecules of gas. They're colored here just black and white. You can imagine that the black ones are nitrogen and the white ones are oxygen. It doesn't really matter. So that's fine. The barrier separates them. We take away the barrier, and before too long, some of the white molecules are on the black side, and some of the black molecules are on the white side. And if you wait a little bit longer, everything is all jumbled together. Well, okay. And in fact, no matter how long you wait, they won't recluster into that original pattern. they'll eventually just sort of reach a maximum amount of disorder, and that's about it. But you wouldn't get confused as to what direction this, if these were 3 frames in a film, you have no doubt as to which way it goes. Okay, so as far as that goes, that's fine. But, you know, if you have this highly ordered system, you can correctly predict that in the future you're going to have a disordered system. But it doesn't work the other way around. If you have, and now the thingy's not working, but that's all right. If you have something like this, and try to guess, well, what came before that? Well, you don't know. You have no way of knowing that it was preceded by this. To take another example, if you have an ice cube at room temperature, you can correctly and easily predict that in a few minutes you will have a puddle of water. But if you have a puddle of water, if you walk into the room and see a puddle of water, you cannot guess what came before the puddle of water. For all you know, it may have always been a puddle of water. So what physicists say, and I mean, this isn't my area of expertise, but from what I've read, at least according to some physicists, this is a problem. There's no retrodiction. If thermodynamics really explained, if the second law of thermodynamics and these entropy arguments were a complete explanation, you'd think it would work both ways. You'd think you could sort of predict backwards. Also, yes, if you have a highly ordered system, it will give way to a disordered system. But why would you just happen to have a highly ordered system? Does it mean that in the remote past everything was really, really ordered everywhere? I don't know. Does it have to do with how the universe began? Why would there have been low entropy in the first place? Now I could segue into some technical stuff about the microwave background radiation and how the universe got started. I'll leave that aside for the moment. But this at least raises some things for us to ponder. Also, these things I've been talking about illustrate the thermodynamic arrow of time, but that seems to be only a part of the puzzle, because there seem to be other arrows of time as well. Cosmologists will point out that we have the Big Bang 14, give or take, billion years ago. So we have a very small universe, then a medium-sized universe, then this bigger universe we're in now. So that seems to give an order, a sequence. That seems to define one arrow of time. And your mind seems to do it as well, right? We might call this the psychological arrow of time. We remember the past, but not the future. Why is that? I know that sounds funny, doesn't it? But why are we only aware of one half of this? So there's something perhaps a bit funny going on in our minds that, and notice, by the way, that it's the opposite, it works the opposite way from the thermodynamic arrow. We can, with the thermodynamic arrow, we can make these very clever predictions about what's going to happen next, that an ice cube will become a puddle. But your minds sort of work backwards. Like if I ask you, all right, so what are the election results going to be in 2012? Well, you don't know. I mean, you can guess. However, if I ask you about 2008, all you have to do is look it up or recall it, right? So it's funny. We seem to be able to access sort of backwards. That's what our minds do, even though retrodiction is terrible when we try to do it sort of on the thermodynamic side. How are these arrows related to each other? Well,